Okay, let's get started. And today is the last module of this week-long training. We start from very basics of data science. We talk about EDA, exploratory data analysis with pandas. We talk about graph analytics. We also try to do some modeling with scikit-learn. And today we'll be doing some deep learning. And when I say deep learning, it's mostly deep neural network based machine learning with Keras. So probably, I know you're probably not familiar with Keras, but you probably know TensorFlow. Keras is a version 2 of TensorFlow, more or less. And I'll talk a bit more about history of Keras, which is actually, there's an interesting back and forth with Keras and TensorFlow. We'll get into that a bit later. So there are two very good references for beginners. Also, actually, the book that are written by Ian Goodfellow and others. The middle one the I'm not sure, is he getting, no, he getting the Turing Award, but not the Nobel Prize, right? I'm not sure. Someone can check. Probably no, he's not. Ian Goodfellow and Aaron Corvin, I'm sorry, hopefully Corviel, and Joshua Bengio. These are pretty big names in deep learning community. And this book by Ian, by these three authors is a so-called Bible of deep learning. People always give names like that for programming books. The second one is a YouTube video, a series of YouTube video made by Grant Sanderson. Probably you heard about the 3 Blue 1 Brown, which is a very, very good series of video with diagrams and all other things and animations showing you how deep neural network works. And if you are a beginner, you're interested in learning more about basics of neural networks, this series, probably 3 or 4, I forgot the exact number of series, it's very good. It's worth the time, probably totally an hour or so to sit through all those videos. So we already talked about this. So today we'll be focused on deep learning, which is a subgroup of machine learning, a subset of machine learning. And it's focusing on using neural networks to try to find the functions to help you to map the input to the output. Yes, I already, I showed you this most important slide about the machine learning. So basically, you're trying to, given the x and y, which is the input and output, we want to approximate a function f by optimizing or minimizing the error, the absolute value of fx minus y. So essentially, the same idea goes for deep learning. The only difference that the function, the form of the function here in deep learning, it's already given, which is, it's kind of not clear to those who are just getting started with deep learning. They may think it's something like, magic, but it's kind of like very systematic way of finding the function. Machine learning will require some algorithms, some tweaks, some smartness, as mathematical reasoning and logic within the math. But for deep learning, it's brute force mostly. But of course, we are trying different ways to build up this neural network. It's more like arts. But essentially, after you get a neural network ready, the rest of the work is just the computing power and data, of course. So what is a deep learning? The reason why deep learning is introduced is because the limitations of the traditional machine learning methods. One very simple example is that for in computer science, especially in computer vision, is to find a particular patterns inside an image. So, for example, someone give you a picture. Then if technically it's possible for the computer vision to detect certain geometrical shapes inside of this image. And based on that shape, you can tell if there is a car inlet or if there is a bicycle inlet or something else. It's mostly done with so-called convolution method. So the computer scientists back then, they created all different filters, like circular filters, rectangular filters, different shape of filters to scan the image. it's almost naively to think about, when you see the scanning of an image, that you have a pretty high confidence that this image contains two circles. You may estimate, you may guess that there is a bicycle in it. So things like this was done by computer scientists based on our understanding of this world, based on the traditional computer vision technologies. So this kind of method to create this kind of filters is called feature engineering. We needed to extract all the key features of the object before we are able to do anything about it. You all probably tried out the iris dataset, the example. So when you go to do some research on this iris dataset, you don't take pictures back then. Many years ago, that's when people start collecting data. Someone just get to the field, use a ruler that measures the sepal length, sepal width, petal length, petal width. Why you think it's important? Because based on your study, based on years and years expertise, knowledge and learning and training in the field, you notice that there are these four quantities can give you a unique combination, can help you to decide if this particular iris belongs to this group or that group or the other group. So that the two steps. The first step about understanding these four numbers inside iris dataset, assuming you all have tried that one. Understanding those four numbers are important. That's step one. That requires your domain knowledge. You have to be trained in the field to understand those four quantities are important. The second step is to go to the field to do the measurements. That's when you do the data extraction from the data. Essentially, it's just whatever you use to measure that. This action you take for you to extract that information you need is data engineering, data feature extraction. So similarly, when I give you ask you to compare horse and donkeys, right? It's easy to measure the ear length and also the height and weight, etc. If you get those features, if you only have two animals to tell the difference, it's doable. You just go out there, measure the handout, a horse, regular handout horse and regular handout donkey's height and length and weight and ear length, whatever. You can probably have a very nice model to separate those two. Those numbers I just told you is based on my observation. Those are the features needed. So all of this needed to rely on human knowledge and some expertise in the field. Okay. Now, deep learning doesn't need that. Deep learning simply takes the data you may have, for example, image, which is the most commonly used data, which is readily available with all the cameras we have, all the sensors we have, all kind of cameras we have. Pictures are most commonly, mostly commonly used way to share information because we are visual animals. Whenever we have a picture, we can see things more quickly than reading through stuff. So that's why people always say a picture worth 1,000 words, right? So like 70 to 80% of information we acquire from outside from our eyes. That's a vision information. And deep learning, especially for computer vision kind of applications, when you provide the data, you don't need to go in the field, measure the length. You take a picture. The picture will capture a lot of features, information. Of course, you can capture not just one. You can capture pictures from different angles and from different perspectives. You can send it to me, and of course, based on a lot of data you're collecting, the deep neural network can extract those features like circles, different color shapes, automatically. But when I say automatically, of course, there are many catches there. But assuming we're not getting there yet, let's assuming we are trying to compare deep learning deep learning against traditional machine learning. You don't need to do the go to the field and measure all the particular things that you think is important. Just take the raw data and without doing extra thing about the raw data. You don't need to pick particular columns of data, etc. Just feed it into a deep neural network. It will handle all that for you. So that's one of the major advantage of deep neural network or deep learning method. Basically, you don't need to be that smart to know what's going on underneath for the data set itself. So it's on the technical level, the implementation of deep learning, actually is starting from the very straightforward, the simplest deep neural network. It's just a connection of layers and layers of neurons connecting to each other, one after another. Starting from input all the way to the output you're expecting, you insert multiple layers of neurons, which are just simply visually, you can think those are just layers of neurons, but essentially just a matrix of containing all the parameters and help to map your input to the output. It's not simply the matrix itself, it's an operational matrix. It combines the linear combinations, linear weighted average plus a nonlinear terms. Otherwise, your function will, if you only do the linear on each level, if you're familiar with the linear algebra, all the linear combination of the linear terms, you ended up with a linear space. So your final function can only be linear function, which is not able to resolve all the things that are in the nonlinear world that we are dealing on a daily basis. So all the functions that deep neural network is representing, deep neural networks are representing, they are a very complex, nested, and nonlinear functions. Every layer you build, you add another nested function, another level of nest inside. So you have function calls function calls function, and on each layer you have a weighted average of all the neurons for the data on it. So I'll get into some example a bit later. So one big benefit of this deep learning is that it's able to handle tons and tons of data. It's not, of course, with more data means more computation, which actually dramatically changes the way how the traditional machine learning is handling, because traditional machine learning method will not scale well with the dimension. As I mentioned, for a given picture, actually, if you look at a given picture, it's not just 2-dimensional anymore. For a given picture with 300 by 300, it's a very small picture. Think about the resolution now your phone can take. You can easily get to, I'm not sure, for the camera, latest iPhone camera, you can get multiple megabytes. I forgot exactly the number, but could be easily several thousand times several thousand. Let's just consider it's a very small picture, 300 times 300, right? That's already 90,000 pixels. When you're handling the images, every pixel actually is a completely independent degree of freedom. There's no one can tell you that one pixel have to rely on the other pixel. They are completely independent. That means you have 90,000 dimensions. Think about that. You have 90,000 dimensions. For the problem we are looking at, like iris dataset, how many dimensions, how many features we have? We only have 4: petal width, petal length, sepal width, sepal length. And for the diabetes example I showed you early on, it's just like 5, 6, whatever, 7. Or the wine data set is probably 6 or 7, 9, 10, whatever. Just very small amount of data set. That's the problem that a regular machine learning model can handle. If you give a model like thousands of dimensions, there's no easy way they can handle that data directly. Of course, we talk about dimension PCA, principal component analysis, and some other method you can use to reduce the dimension, but at the same time, you reduce a lot of fine information as well. So you want to keep the raw data there, trying to resolve every dimension possible, while you want to do some analysis, do some feature extraction in the process. So that's the hard part. Deep learning can handle that in its own way, and we'll learn how to do that. So you can look into other examples here. I'll get into. This is an analogy people have been making, trying to compare the so-called deep neural network or artificial neural network to a neural network. We have people probably are more familiar with the diagram to the left here. So I'm not an expert, but this is basically what I learned from other people's work. It's definitely not my innovation. All the neurons, you don't have a long single string there. There might be neurons just connecting them. Each neurons are connecting to each other loosely. One neuron gets a signal from previous one. When certain condition happens, this neuron will activate this, and the signal will transport through this axon, and then the end of this neuron will receive that, process it, send a signal to another one. All these signal happens like electronic signals. That's exactly why this neural link, the neural link, that's what Elon Musk is doing. It's working because electronic signals, if you have a very sensitive sensors, you can capture those electronic signals. You can capture what people are thinking in mind. People have been doing this research for years, right? You probably know more than I do. But the neural link is doing something more dramatic by capturing the image and doing some analysis. That's something, I'm not an expert, but this is relevant to this neural network in the sense that every neuron here could be represented with each neuron inside this neural network. You have multiple neurons with these layers. You transmit information from all the way to the left, all the way to the right. Every time there is a so-called activation function, kind of like a conditional, like threshold physically. So there's so-called activation function. Whenever the signal is reaching to a certain level, it's activated and send the signal to the next. This is a fully connected neural network. It's kind of like a graph, but it's not fully connected to all the other nodes, but it's fully connected to all the nodes to the next and the previous layer. That's call it fully connected layer or fully connected neural network, or so-called multi-perception layers. This is the simplest and the most widely studied neural network. There are different topologies, but this is the starting point. It's called a dense layer. As long as every neuron is fully connected to the previous layer or the other next layer, this is called a fully connected layer or a dense layer. So we have a dense layer neural network like this. Just visually, it's just like this, nothing more, nothing less. I'm already showing you the full picture of a deep neural network with 4 neurons on each layer with 2 hidden layers. That's it. This is a really functional neural network. Now, the only thing I don't have is just the weights there. For different problems, you have to train your model. These weights will be able to help you. If you have a lot of things, a lot of data with a lot of details you need to resolve, this H neurons won't be able to capture all the details. You have to increase the number of neurons, increase the number of layers, and then you can handle more complicated scenarios. It's highly depending on the features you want to extract here. If only you want to extract not so, so complicated features, you don't need that complicated neural network because the information you gained and the information contained in this neural network is proportional to the information your object is, your particular problem contains. You don't really need to overcomplicate, make things more overcomplicated than needed, right? So that's the a simple analogy between neurons and neural network. This is about treating or considering whatever you do, but we don't get into the proof ourselves, but we assume these are valid. They already proved that for the neural network, as simple as a multi-layer perception, the one I showed previously, you don't need to have a very complicated topology here. Just very simple multi-layer perception, one layer after layer. You can build a function approximator. This function approximator is so powerful that no matter how complicated this function, this mapping function could be, it's able to help you do the mapping. So that's the mathematical power behind all the magics happening now with all the neural network, because this neural network that we are going to build could be working as a universal approximator. You don't need to scratch your heads to figure out if it is x plus b or x squared plus bx plus c. You just need to figure out how to tweak all the parameters, and then you get a neural network setup. Of course, there are many details to get in, but this concept, this idea is very, very powerful. Of course, the definition of, actually this is not just one. This is the universal approximation theory about using this f function as approximation for almost all the non-singular, whatever. There are some very special functions that are kind of hard to, like a delta function, those kind of crazy functions. Probably this one might not be able to handle. But for most of the functions we see describing all the natural phenomena, this is more than enough to handle all those functions. There's one more thing here, which is beyond just the using fx for describing the function. People have also proved that for most, a lot of very generic cases, this derivative of x itself actually can approximate the derivative of the real function as well, which is really, really powerful when you're doing scientific computing, because when you're doing this numerical computational stuff, solving with partial differential equations, it's essentially an equation for derivatives. In many, many partial differential equations, just equations for those derivatives. If you can assume a function that can not only approximate the mapping function between A to B, but also the derivatives, that means you can use neural network to approximate all the mathematical equations that you are using in physics, chemistry, whatever. That's the foundation. Actually, of course, both of them, not just one, both of them are actually building the foundation for the so-called scientific machine learning. People are using this theorem as the proof that we can learn all the natural laws through the neural network. Okay, this is an extremely hot area, so-called AI for science. If you go online, everyone's doing that nowadays. Almost all the AI people, if they are not interested in doing LLM, then they must be doing something like AI for science. And that's the way how to really make this neural network connected with the natural phenomena happening around us. You can use AI to study climate change and other things. And you can probably read some news from NVIDIA. They already built a very powerful neural network to study the climate change. And that's like 1,000 times faster, efficient than a traditional way of doing this to solve the equations. Because when you write the mathematical equation, like the theoretical equation I showed you all, you have two ways to solve problems, like theory-driven and data-driven. For the theory-driven equations, the reason why it's so complicated, because in the real life, you have to deal with different physical phenomena at different scales. At a large scale, and you can assume everything is continuous, and which is fine. But then if you want to deal with micro scales, then you need to deal with all the reactions, all the things like that. The spatial scale will be dramatically different. Now, if you want to really evolve this function forward with time to make predictions, you have to resolve both the detail and fine scale and also the large scale. Large scale means the spatial domain will be big, and the resolution needs to be very small for small scale. So that makes your whole simulation very, very expensive to do this real-world simulation, unless you have some very special problem and everything is continuous, it's nice, but those are mostly trivial problems. Mathematically, you can even find as an analytical solution for those. But numerically, when you're trying to combine all this together, this so-called multi-scale problem is actually killing all the numerical simulations as far as efficiency and time is concerned. But neural network can handle this. It's kind of crazily efficient. So that's why many, many researchers that even very famous theoretical physicists that jump in to neural network to figure out how this can help us to answer some ultimate questions we have. Because in many, many questions, there is no analytical solution. All you can do is just do numerical simulations. And neural network can probably help us to speed up this process dramatically. Okay. So these are all the foundations for all the things we'll be talking about today. Again, for neural network training, since we are mostly focused on supervised learning, we are not doing any unsupervised learning in this class, in this workshop. For supervised learning, you have two steps, as I mentioned previously yesterday. On the training state, given the input and output, you're trying to best fit f function. Now, inference, that's when you start using this function. When the function's error, when you're doing the training, you keep monitoring the error of the function. If the error of the function is getting smaller and smaller, you might start using this function instead of keep training that. Now, in the inference phase, you give input under this function, and then you predict output. That's how you use your model to get some output and deliverables. Okay. Now we switch gear to computer vision problem, because this one is computer vision problem is more visual, and you can easily see how deep learning is working. Actually, deep learning nowadays use a lot to do the number crunching, which solving PDEs, doing all those kind of stuff. But we're not getting into that. We'll be looking at a computer vision problem, and there will be a couple of examples. Look at this picture. This is from the Stanford CS231 course. It's a series of some course and people posted on YouTube and other online course website. It gives a very good introductory level materials to computer vision and deep learning, which is very, very good. You can search that course yourself. So this is one very simple, very interesting, when I first learned this, I keep this for the credit for this course. Now that you can easily create similar diagrams with other, with material from other courses, but I think it's good to keep it here. Now, given this image, we can see that it's a cat sitting on top of a trunk of a tree or somewhere with all the branches in the back end, right? That's what we see. Now, for the computer, this is not what the computer can see. Computers see all this, right? Because it's a 3 layers RGB channel. For the regular image, you can have a 4th channel, but this RGB channel, you have 3 layers of these numbers for each channel: R, red, green, and blue. By combining them, you get a colorful picture like this. Now, if we want to build a model to take this as input and predict if it's a cat, dog, or hand, or mark, assuming we have 4 groups of data we want to train our model. Our model knows nothing about it. If you build a model from scratch, your model knows nothing about anything. It's just empty. You start from scratch. When you start from scratch, you need to collect all kinds of data sets. Like if you want to train a model then to recognize 4 categories of images, you need to train, or you need to prepare data in 4 categories of images, 4 categories of data. You need to actually it's a 50 or 40. I don't know exact number, but you can always try out. Of course, the more the better. Probably 40 or 100 images of a cat, and it's comparably 100 images of dog, 100 images of hand, 100 images of mug, of different kind of mugs, different kind of hands and dogs and cats. But you need all the data to train the model. But for the model to do this, assuming its model is trained, now what the model can do? The model will take this, assuming this will be like just one index. Don't worry about RGB, it's just one channel, like black and white channel. It will need to take this matrix, very big matrix, depending on the resolution of the image you're handling, and turn that into a vector of 4 numbers. Each number representing the percentage of this particular image gets into the particular category. So given these 4 numbers, I can say I have 82% of confidence. It's like, probabilities, like 82% likely to be a cat. It can never be 100%. As I mentioned yesterday, you can never be 100% sure because you always have errors and all the other randomness in the model. But this is already pretty good. You can, based on these 4 numbers, you can say, okay, it's very likely to be a cat. That your prediction is a cat. That's how you do it. So the trained model will take this as the input and output 4 numbers. Now the question is, how can a model compress that much information into just 4 numbers and give you the information you need? Right? So that's the magic. Assuming, just very simple, 256, 250, it's just like a square, it's very small square matrix. You use that as input because the image to the computer is nothing more than a matrix. It's simply just a collection of data in a 2-dimensional, structure, and then if you just flatten it out, it's just one big gigantic array. If you put all the rows into one row, and then you have a gigantic array, there's no way someone can tell it's a cat. Just look at the numbers, right? But that doesn't matter. For computers, they can take that and convert that into a 4-element vector. So this function, if you assume you now, because I already told you, deep neural network itself is like a function. So this function can take a lot of data and compress that into only 4 numbers, which is a lot of compression going on. That's one thing. And a lot of distilling going on to extract information you need. That's another thing. So compression and feature extraction, that's something happening automatically. inside of this whole operation. Okay. Now, how does that happen? This is give you a very intuitive diagram. I'll go through this slowly with you all. So this is very important for you to understand what's going on for deep learning, and it's some ideas about backward propagation also coming up from this diagram. So I'll go slowly with this. So first thing to understand what all these diagrams means, then you probably can follow me easily. This is assuming this is a data set. Each row is your one entry, assuming it's one image. Each row is one image, okay? All the boxes here representing individual pixels of an image. Consider the first row here is a cat. This is the second row here representing a dog. This circle is just a label telling me that this is a cat. That's the result. That's something you're expecting. That's your Y. All these blocks are your X. You want to build your function, your neural network, to map this to this. And you want to make this prediction correctly. This representing, for example, a hand. This should be a value showing the hand, etc. So this is a data set. So what you do when you build a neural network, you feed in your neural network this data set, one after the other. Of course, just like when you're reading books, every time you just read a book once, you probably after you finish, your memory is not as strongly impressed, and then you remember everything. You go back to read it again. So that's why for deep neural network training, you need to do this many, many, many times. Every time you call it an epoch, E-P-O-C-H. I learned that word in this. Of course, epoch means something else, but in here, every time when you feed all your data set into your neural network once, it's called one epoch. It's pretty common to have 1,000 epochs going on to train a neural network. So it's not the smartness of the machine, it's just the hard work for the machine to learn. It's just, for computers, doing this very, very fast. It's kind of like if someone's sitting there, someone give you a book, you keep reading this like 1,000 times, at some point you'll get bored, but the machine never gets bored, right? So that's the power of all this thing, AI and machine learning. Given this time, now let's take this one first data, which is just an image. I flattened that into one long array, row after row. I put that into one long array. I can easily handle that. For the two-dimensional, I can handle that in a different neural network. But for this multi-layer perception, that's one I told you, need multiple layers. It's better to have everything into one big array. It's fine because for machines, it doesn't need to have everything organized perfectly as a 2D matrix like what we saw before. We take this data from the first image. That's my X. I laid out like this, like a big array. Good. And then I initialize all my initial values. These are just give them a random number here, give them a weight. So 0.1, 0.01, 0.0, 0.1, whatever. We just give them a weight randomly, initially random. Because I don't know what value I should give them. I just give it a random number, which is fine. No matter what, after I give the random number, I can start doing the weighted average. For example, for each one, I get this value. I multiply this, and then this could be the same here. You can do the multiplication of each one with all, the weight is associated with each link, and then you can do the multiplication of this value with this value for this, for this, then you get a weighted average sitting on this one. So you get a weighted average plus some function, which function we simply, let's consider, don't worry about that function. Let's just consider we are doing a weighted average. We get a weighted average for the first neuron. By getting the values, you can do normalization. You can turn all these values. So these pixels are always going from 0 to 255. That's RGB value, 0 to 255. But you can normalize all this to go from, say, 0 to 1. It's your choice. You can just go 0 to 205. It's fine. Let's assume you already normalize all these values going from 0 to 1. So all these values, all these values will multiply corresponding weights and give you a new value here. And then this will be multiplying the weights itself and get a weighted average for the final output. So even if you have a random setting for all the weights you have here, you'll get some output no matter what. It's simply just weighted average of this, each one, and a weighted average of all these ones. You get some output. Since all the weights you give to all these neurons are just random. The first output here definitely is a random number. But it's fine. You get something, right? You compare this to the target output. Notice there is a big error here because you're expecting some random number. There's no way that you can the first guess will give you the correct results. So that's fine. Now, what you do next? You increase the weight of this one. Let's assume, say, this guy is very important. I don't care. Let's assume it's the very first one. It's very important. So you'll give more weight to this one, and all the others you keep them untouched. By increasing the weight to this guy, you get another expected output calculated because you increase the weight, the whole thing needs to be calculated. Okay, you get the new weight. The new weight and the target compare. Now you get an even bigger error. What does it mean? What should you do? You decrease this weight. That's the trick. That's the whole trick of backward propagation. After you decrease trick, the reason why this is happening because the mathematical reasoning behind this. When we are getting close to the top of something, when you know on one direction it's going down, it's very likely another direction will going up. So when you increase this, it's almost guaranteed unless you are very lucky at the top, at the top already. But in most cases, in general, if you decrease it, if you increase this weight, the error is increasing. Then you decrease this error, guaranteed to be decreasing in a certain range. If you don't do very rapid decreasing, because we are expecting this continuous function that we are trying to approximate don't have a rapid jumps. And it's very unlikely you'll be experiencing that at this very special case. So when you decrease that, it's very likely you could decrease. So that's good. Let's keep this new value and do all this one by one. You are doing training. That's when you train, you're tweaking all these parameters for all these neurons and find the best neuron, a combination of these neurons, and give you minimized error. After you get this down, you can do all this one by one. Right? Then you feed in the new data and do this again. After you continue doing this, you get all the weights for all the neurons that give you the minimized error for all this data set. After you train this many times. So this trick to increase and decreasing, you do this only manually, but mathematically you have a better way to do it. That's called a derivative. Now let's get into this a little bit mathematical, but it's not that complicated. Actually, if you follow me closely. So for this Y3, that's exactly the neural network you'll be dealing with for this class. We're just dealing with mostly the dense layers, which is just like that. Even visually and in practice, it could be just like more neurons or more layers. That's all. So just follow what just mentioned in the previous example. The value of this Y3 will be calculated by the weighted average of this, which is simply Wi, or W1, W0 times X0, or W1 times X1, W2 plus times X2, W3 times X3, sum them up, plus a little bit of bias here. This bias is important for you to make sure you don't, you have the bias also shifted. That's also shifted, the level of your axis value here. So actual bias will be added as actual value. So after you get a weighted average plus the bias, you get some value here. And then this function is called activation function. We'll worry about that later. Just consider it's just nothing. It's considered just one. It's fine. You can just assume you have a weighted average here. You do the same thing for all this, and the corresponding weights for each line will need to be calculated as well. So that's weights, weights 1, 2, 3, but you also have another weight, another weight, a sequence of weight for another neuron, etc. Now you continue doing this. For this one, you need to do the weighted average of all these 4 plus another bias I mean, another bias for each individual. You do all this until you reach to the final output. Now, think about it. What kind of function will this be? If you don't have this activation function, it's simply just a linear combination of all your input, right? It's just a linear combination of the input. Every time you have an extra wi multiply this plus some bias, and then have another layer, you have another weight multiply this whole thing plus. So your x will be simply just keep there. So it will be weighted average of this input give you output. As I mentioned, that's not a good way to do approximation. Approximation we're dealing with needed to be able to handle the nonlinear cases. So that's exactly what this f is. F is trying to introduce linearity to your function. So your function can be more expressive. It should be able to not just representing x plus b, but also x squared plus b, or add e to exponential x plus c, whatever, right? So this activation function will give you the linearity and also working as activation function itself, which is kind of like a threshold. When you reach this threshold, the other next neuron will be activated. Otherwise, the signal will just disappear during the transition state, which means it's not so important signal. Only important signals will be transmitting all the way through your neurons and do something. Those for example, when I look at this thing, there are some other information coming from this side. I don't care. This probably information will disappear during the transition state. I don't take any actions about it or anything about it. But for some important information, I capture it, I take some action. That's the more or less like this f function is trying to provide a threshold. Otherwise, our brain will be so busy, right? For everything I see, for every pixel, kind of like a pixel of information coming from the outside world, if we have to deal with that, then our brain must be burning like a nuclear bomb, So that's more or less like the function, the mathematical model for this. Essentially, this is the universal approximator we just talked about. This is just our fx. Mathematically, that's our fx. We are just trying to tweak all these w and b's to make sure our fx itself can give us a prediction and minimize fx minus y. So that's why I also mentioned this neural network is a very, very systematic way for you to find this approximation for your mapping function. Traditional machine learning method cannot do that. We know this nearest neighbor or whatever, classification method, those, you need some algorithm for you to follow. There are many, many other things you cannot easily control. But for this, all you need is just provide an input and output. And this like a machine can automatically figure out the corresponding mapping as long as you get its W and B's tweaked properly. Of course, you can use this to simulate the linear equation as well, like a linear regression model. Yes, so after you get y, no, this yj is just for one layer deep. Yeah, you keep doing this, so y1, y2, y3, y4, then you calculate the z, given this z, whatever, and then finally it will be a function of z, etc. So it's a nested function. That's why I'm saying nested. But every x or every x here, if you like a shipping all the way to the next layer, so you can have nested functions. This x could be replaced by f, sigma, w, whatever, then etc. So you have. No. This yj is a capital case j. This is just representing the intermediate layer. But in the final case, after you get that figured out, then the final mapping function will be going all the way from x1, 2, 3 to final output. This yj is just representing the intermediate layer. This function is just for one layer deep, but it's not going to the output yet. We'll be getting there after you combine all this and move layer after layer to the final step. It's a nested function. I needed to write this down explicitly, then you can probably figure out, right? If you can write down this one as f of sigma W, what you call it different name, W1, 2, 3 might be confusing. It could be because it's a completely different set of weights you need to use. But this will be a multiply Y1, Y2, and Y3 here. Then you get all this figured out, all these values calculated. Exactly. New Y, exactly. This is just each Y is just completely new Y and a new X. You complete new Y, new X, then you, but it's this only mapping this neighboring layers. Yes. Y is, oh, bias is changing for each layer. It just give you extra freedom to tweak all the potential parameters. It's just the way it is, the way how the neural network is designed. When you do this, every layer you might be able to introduce, it might introduce some extra bias, but this one just trying to tweak that particular bias you're introducing and give you extra freedom. And this, because also getting to the mathematical, this is not a guarantee to be a completely homogeneous mapping. If you don't have this, it's like a homogeneous, then you have to pass it through the origin of your system. But it's not guaranteed. Your system might be going up and down because of some errors you're introducing. So this gives you extra freedom. If you don't have this be assuming, let's assuming everything, when my x, all x is 0, your y is guaranteed to be 0, but in some cases it's not. So you're not guaranteed to passing through your origin, and that's the extra bias will give you the freedom to adjust your errors in your data. That's the error you're introducing in your data, that this one is help you to matching that extra error for each layer. Yes. Neural network itself is a very common name, but deep neural network is mostly referring to the neural networks with more than 2 hidden layers. If it's just one hidden layer, you cannot call it deep. It's just a perceptron. It's called a forward perceptron. Many years ago, when before people get into hidden or multiple hidden layers, they're just using one layer in between and using this to do the map. But it turns out it's not very efficient, and also it's not so expressive. If you don't have these extra layers and that necessary function to help you to express your function, f(x). Okay. It's the number of layers, that's a so-called hyperparameter inside a deep neural network construction. That's something you need to tune. For different problems, number of layers are different. It's interesting. Microsoft, once they came up with a 1,000 layer neural network, 1,000 layers. Think about it, 1,000. Think about how complicated this function could be. But every layer, they call it a very deep layer, but every layer, they don't have so many neurons. There are some very wide neural network that have very big layers, but not so many layers. But totally, the total number of neurons is proportional to the computational task computation you need to do for the training, because that's exactly when you try to do the training, you want to figure out all the weights for each one, and the more neurons you have, the more computational costs for training the neural network. So, nothing comes for free, and it's also coming with cost. So either you get a very wide network with less layers, or a very deep layer, a bit deep neural network, but with not so many layers between. There are also some other variations in between, but anyway, so that's the mathematical structure. So this is essentially the approximator we talk about, fx. No matter how complicated your neural network is, the function itself could be easily expressed in that. Almost all the neural networks work in that way. The main difference is this f function. This is called the activation function. This could be very simple function, could be very complicated function. Of course, when you have millions and millions, or sometimes billions of parameters to tune, making this a simple function usually give you the actual advantage. It will be much cheaper to calculate. Right? We'll get into that in a second. Now, after we get that function, assuming we have this y defined, then let's just look at just 2 neighboring layers. since you get all the things figured out, the mathematical expression will be too lengthy. Let's assuming these are already inside the layer, not the input data. That's one of the hidden layers. This will be the next layer. Just layer 1, layer 2. Those are both hidden layers. I can define my loss function or my error, which is in the statement I mentioned yesterday, it's fx minus y absolute value. But here we define this squared, which actually is just like a mean squared error. We try to calculate the expected value. Which one expected? Y. This one, the expected, is the one calculated using your neural network. The other one is a value you have in your data set. So this is like fx, this is like y. But here, instead of absolute value, I have a squared and a sum of squared. Actually, it's not equivalent, but it's similarly. We can define the error this one as well. It's mean squared error. The reason there's a 1/2 is because we need to do some derivatives, and this 2 and this 2 will cancel out. So we put a 1/2 here. Okay, so that's a very commonly used way to define the errors, the loss function. Now, when we try to do optimization, like I showed you the diagrams previously, multiple diagrams previously, we want to minimize this L by changing these weights, right? We are changing the weights. Remember what we are trying to do here? We are changing the weights. That's the weight we are changing for the layer. Oh, I'm sorry. No, activation function itself is just it's analytical function that you can write it down explicitly as a mathematical function. That's activation function. But this L, after you write it down in this way, in the neural network, this function is a known function. Even though it's very complicated, but it's a mathematically known function. You don't know all the weights and biases, but those are the things those are variables. X here, that's what? That's a constant. Y, I'm sorry, this Y from, assuming this is your data, this is this is whichever you use. Let's call this one. This one is the Y you calculate. That's your Y you want to calculate based on your neural network. You can start your weights and biases, all these two as random numbers, like what we did previously. This X itself is a constant. Y prime is a constant. Okay? Y prime itself is a constant. So this is only a function of weights and biases, because that's the thing we want to tweak. X and Y prime, this X is just a function. This Y is just representing the neural network function. But inside this Y, it's only depending on X, W, and B. And Y prime itself is a constant. So when you take derivative, it doesn't matter. It's just a constant given the data point I want to use for training. So this loss function is just a function of W and B, and this function itself is analytical. You can write it down, this function, mathematically. That's the game changer. The reason is that then you can take derivatives, because I want to see how can I change my W so that I can minimize my Y error. Because look at this one, because this is like a square function. Think about a parabolic shape. It's like always like that. When will you get the minimum value? When the partial L, partial W is getting to 0, you get a minimum value. Partial L, partial W getting to 0, you get a minimum value. But to change the direction, so at the very beginning, you don't know what your value is. You want to figure out the direction, how you want to change your W so that you can minimize this L. To minimize this L, you take a derivative of this W and add an extra negative sign to it. That's how you change it. Why? Let me think about it. Let's just don't look at this one. Just look at partial L, partial W. W is weight, right? When you increase the weight and the L is increasing, this whole thing is positive. That's like a parabolic monotonic increasing function. That's when W is increasing and L is increasing. That means when you increase your weight, the error is increasing. What should you do? You decrease your weight. That's why there's a negative sign here. So this tells you how you change your W. Instead of doing that manually, this gives you a mathematical formulation to know which direction you want to change your W. Now think about the other case. When the Wi, when the weight, remember the diagram I showed you all, when the weight is increasing, but L is decreasing. You want to increase your weight because you want to decrease your L anyway. So in that case, partial L, partial W, it will be a negative number. Then delta W will be a positive number. That means you need to increase your W. So that's the power of math here. This derivative gives you not only the direction, but also how much you want to increase your weight. There is one extra parameter here called alpha here. Alpha is called a step function or step length. So it tells you how big your stride should be for you to go forward. You can control this. You can make it big and make it small. At the very beginning, you can make this very big. But gradually, when you're getting closer to the bottom of this minimum, you don't want your stride to be too big. You might be striding over to the other side, right? You want to, when you're getting closer and closer to the bottom, you want to minimize your stride. So you're getting closer and closer to it. Otherwise, you'll go to another slope, which is not a good idea. This is not something that machine learning community, computer science are doing. This has been done for many, many years, in optimization series. If you get any book of numerical optimization, this is called a gradient descent. It's a standard way to figure out the direction and also the how big your step should be when you're trying to minimize the function. So things are getting easier now. If you think about now, that's starting from the very beginning. You start to initialize your neural network with all the random numbers. And then you take derivative of your loss function against your weights and biases. You get this kind of function figured out. And then you figure out when, start with a random number, and then you know how to change all individual bias for each layer. You do this layer by layer, you can update your bias. Whenever you get new data points, you can do this. Every time you pass through your image once, you update your weights once. Keep doing this many, many, many times until your error L is getting to minimum. Of course, you probably will never reach to absolute, zero, because you always have some errors there. But in many, many cases, by just utilizing this power of derivative, you can get to the point. This is a backward propagation that get Jeffrey Hinton the Nobel Prize. So sounds simple, but that's what it is. Okay, before we get into next one, any questions so far? Okay, since we have a lot of materials, I mean, not just food, but also materials in the slides, so we needed to move on. Otherwise, I wouldn't be able to finish all the stuff I really want to show you all. So let's switch gear to convolutional neural network. And this is different from the previous one. We talk about like multi-layer perceptron. This is a more about dealing with 2D information. Essential idea is kind of similar. You have neural network created, but this one, it's kind of like structure, topology kind of different, but it's still the similar idea. You can build a mathematical approximator, and all you're trying to do, you're trying to find all the weights and biases, and then you solve your problem. But weights and biases are not like the weights and biases we saw in the layers. Those weights and biases now are stored in these so-called filters. Okay, so we'll get into that. So convolution neural network, CNN, is getting really, really powerful, and mainly because it's able to not capture the one-dimensional data. Because for images, especially for images, even though all the pixels, every pixel itself is independent, but when you put multiple pixels together, you may have some patterns there. They are independent, but they have some association. Graphically or computational, based on visually, they have some association. So that's why if we just do the point-to-point association, like if you just simply doing the point-to-point, like one-dimensional array kind of thing, you are losing the spatial connections between the neighboring rows. You will lose that kind of information. So that's why people design this filtering, which actually has been used, like the one I mentioned before. You design filters to scan the images so that you can see if this particular rectangular shape or circular shape give you some matching pattern on this image. If, assuming you have a pattern of a circle, when you scan this image, whenever there is a similar pattern of the circle showing up, numerically, there will be some peak values showing up. Okay, that's when you have a overlapping matching of this pattern. Then when you do the element-wise multiplication for matrix, this is simply doing the element-wise multiplication. You're not doing the matrix multiplication. Simply doing element 1 times element 1 plus element 2 multiply element 2, etc. This is not a matrix multiplication. Then when you have a big value, that means this pattern in your kernel is capturing some pattern there, and you get a maximum value here. So when you scan using this pattern scanning around, you might see some value is small, some value is big, but when the value is bigger, it's very likely whatever shows up in this pattern. Now you can think about this visually. It's like a small slope on this side and big slope on this side. Then that means at some place, if this value is big, there is a similar patterns going on at some place on the original image. That's a convolution in 2D. What does that mean, basically? Now think about it this way. So your kernel here is like a cross figure. If you visually think about it, it's like a cross. If you visualize it on an image visualizer, it's just a cross, right? Now you scan this input with this kernel granularly, you get this figure. Now look at the 4, 4, 4. All these 4s, those are the places that you have a highly more likely matching pattern with this X. If you look at it this way, well, even though it's not a perfect matching, but it's higher than some other places compared to 2 or 3 or some other values. So this will give you some information about these areas. And these areas in your figure is more likely to have this kind of pattern than other areas. That's how you extract certain features. This filter could be many different shapes. If you have like a bigger filter, you can have a circular shape or different kind of shapes. And that's how you do the feature extraction. Now, when you use a convolutional neural network, all these numbers starting with random numbers. You don't know what they are. After you training, after you provide all the input and output, all these kernels will be trained into patterns that can match certain patterns in your figure. For example, if it's a cat, it's likely some of the patterns here will be matching some part of the cat's either ears or tails, etc. So that's kind of interesting way to tweak all your kernels by training your model many through all the images you have many times. This kind of kernels will be consolidated into those kernels that can capture the key features of the image you have. This is just show you the forward example. Assuming I already have the kernel here, this is what you will get. But in the training process, these are random numbers. I need to train this so that I can predict some output like this. Okay. For example, this is how convolution works. This is my kernel. It could be complicated, but it's just visually how it works. This could be a little slash and backslash. These are two different kernels. When I scan my image with this kernel, this is my final output based on the scanning. Well, to human eyes, definitely we probably wouldn't be able to see many differences between these two. But for computers, there are two dramatic different images. This is how convolution is applied on images as a forward processing. Assuming this filter is already trained somewhere, and then you can do this. Before I move to the next one, next animation, I'll just show you this activation function. That's an F, lowercase f, that we are talking about. Many developers started with this sort of sigmoid, which actually maps all your input, maps whatever your input is to a value between 0 and 1. And this can give you a kind of estimation about the probability because it's in the range of 0 and 1. It maps that into that range. tangent edge function will give you map your, no matter what your x value is, to -1 to 1, so that it can give you a good range of output, and you can use that to do some other transformations. These are good, and people have been using this, previously, the first many years of development in deep neural networks, people have been using this too as a non-linear function to help you to introduce a non-linearity, which is exponential function here. This tangent edge is also exponential function, so that you can have a nice, approximation for all nonlinear functions. Starting from, I'm not sure when, that's probably first paper out on the AlexNet. People started using this so-called ReLU. This is the most popular activating function nowadays. The reason why is, first, it's very easy. ReLU function itself is simply 0 when the x is less than 0, whatever your input x is. When your x is greater than 0, it's simply your x. So y is equal to x. It's just like this curve, y equals x, like 45 degrees line like this. And not only this one, but also the derivative of this. Whenever it's x less than 0, derivative is simply 0. When it's x greater than 0, your derivative is simply 1. It's a constant. dx is simply 1. So it gives you a very nice way, because when you calculate the, when you're trying to evaluate w and b's, you need to take derivatives of the partial L, partial w, right? You need to do a lot of derivatives like this. And this derivative is a constant. Now, some question may ask, it looks like this is like a linear, but where is the nonlinearity coming from? That's coming from this 0 point. That's where the nonlinearity is, a small kink, introducing this nonlinearity in this capital F function that we are trying to find. The same techniques are used a lot in finite element method. In the finite element method, we usually use these triangular shapes to approximate as a basis functions, and those could be introduced to representing this nonlinear, because this point here is nonlinear. It's kind of, kind of hard to see, but because there's no continuous derivative, this actual value will add this linearity to the whole function, makes the total approximation function more expressive. Recent years, there are so-called leaky ReLU start become popular. On the positive side, it's exactly the same as the ReLU, but on the negative side, it's not simply 0, because this seems to be more strict. It's more restrictive. They want this function to be able to provide some information on the negative side. So instead of using 0 as on the negative side, the function here is a 0.01. It's like 10% of the value you input. So when you take derivative, it's still constant, but it's not 0 anymore. So you'll have some information from negative side leak into. That's why it's called a leaky ReLU instead of ReLU. There are some other functions, but again, this is kind of similar to leaky ReLU. Explosion. I'm sorry, it's exponential. I'm sorry, my count is not working. It's leaky ReLU, but it still give you some extra curvature along this line near the 0 area. But the main benefit is that it's smoother in this zeros area, in the area where this zeros happens, but it's more expensive. There are some applications for this. People are arguing this might be working, but leaky ReLU and ReLU are still the most popular activation function. Now, this shows you the example for ReLU. What ReLU does, basically just get rid of all the negative values from your, black is the negative values, so just get rid of all the negative values, keep all the white positive values. Kind of like activation function. Whenever you have some negative value, just filter it out. Negative for positive one, just keep them as what it is. So that's what ReLU is trying to do. More or less using 0 as a threshold. Whenever something is greater than 0, good, keep it. Otherwise, just keep everything as 0. As we mentioned, when we go from the image to this 4 or 5 elements of vector that we want to make prediction, we need to do a lot of so-called compression. Compression is kind of like downsampling in many ways. Max pooling is one of the very commonly used downsampling methods. So again, it's using a filter, but this filter is kind of different like previously. You don't need numbers, you just need a shape, like a 2 by 2. Assuming this is my input matrix with a 2x2 filter, max pooling filter. Again, this max pooling filter is an operation. It's not a calculation. You don't need to do any calculations here. It's just trying to find the maximum value in this 2x2 matrix. For example, the first 2x2 matrix here, the maximum value is 6. Good, you keep 6. So the second 2x2 maximum value is 8, you keep 8. And then you keep to find the maximum value here. By doing that, by doing this downsampling, you are downsampling this 4x4 matrix into 2x2 matrix, like 1/4 of the original size. And again, you do this many, many times to make your size small enough. Otherwise, how can you reduce a 256 or 256 matrix into this 4 vectors? You need to do a lot of downsampling like this. This is one of them. This will keep the key information inside this matrix. Maximum value, usually just in most cases representing some key leading information inside matrix. That's how you do the downsampling while keeping some of the key information untouched. Okay. So for this downsampling, simply do this 2-dimensional if you have multiple features, because you have many. Oh, I probably skipped the first part here. These kernels is just one. Depending on how many kernels you can define probably 10 kernels and 100 kernels. It's your choice. So every kernel will capture certain things, and every kernel, after it's processing the original image, you'll get one feature here. So that's why this shows 10 layers of this image, because you have 10 filters. Convolution, do the convolution calculation with the previous layer. You have 10 so-called feature maps. Each feature map is a result of this kernel convolution. It's a processed input. So if you have 10 filters, you'll have 10 feature maps. Usually, in the context of this convolution neural network, you have 10 layers of feature maps. Then, if you apply this max pooling to your 10-layer feature map, the number of layers will not change. This only changes the 2-dimensional space. So that's why your 10 number is still the same. Number of feature maps still the same, because you didn't change your features in the feature. You didn't change your kernels. 10 kernels corresponding to 10 feature maps, and you only change your dimension size, 16 by 16 now, starting from, because it's 2x2. With a stride 2 means you get 2x2. Instead of moving this 1 pixel, you move 2 pixels. That's what stride here means. Because 2x2, you move 2 pixels, you're moving to the next one. And you continue doing that, you can finish the scanning. Okay. This is just a downsampling method, and people give a kind of fancy meaning, a fancy name, but it's useful. So max pooling basically extracts the key information from that. But now, if you look at this compared to the original building picture, there's not much we can tell here. But to a machine, this is already the useful information. A machine can tell some key information from this one. That's something we can never understand, right? We are not our vision system is not trained to deal with that. But for computers, for numbers, just deal with individual pixels, and it's fine. This is so-called a sum pooling. Basically, instead of using the maximum value of the 2x2 matrix, a 2x2 filter, you get the sum of that. You can still have the similar feature. Okay. So next, I'll need to introduce this MNIST dataset, which is very, very famous. The chief scientist, Yann LeCun from Meta, now he's from Meta. Back then, he was from Crown Institute. He's the one first started actually developing deep neural networks, for computer vision problems, and he also helped collect and contributed to this MNIST dataset. It's a collection of 60,000 examples. Totally, actually 70,000 examples like this. With all the characters, handwritten digits. And he collected from all area. I don't know, back then it's kind of hard, but he probably did that manually. Get people in his lab and just ask them to draw all these letters and then keep them in the data. So that's a lot of data. That's 70,000 examples. Each one is very, very small. It's 28 by 28 pixel. From now current standard perspective, it's very, very small. Our screen here is easily 1900. That's probably this 1600. I don't know. It's 1900, and it's pretty big. These are like 28 by 28 pixels. So this is kind of like a hello world problem for deep learning. Everyone start learning C or C++, any program language, they will ask you to write a print hello world, right? You probably have done that. This is kind of like a standard data set you use for deep learning problems. Okay. So using MList, someone developed some very, very good online tool. Let me click this link. You can try it yourself later on. So this is already pre-trained network, convolution neural network. It's more or less like a very first neural network that Jan LeCun proposed. But it's a little bit different, but it doesn't matter. So for us, we just need to see how things are working. It has an input layer, which is here. That's the input layer. And the final output layer. Final output layer has 10 elements. It's a 10-element vector. Input layer is pretty big. I forgot it's probably 32 by 32 or 28 by 28, but it's big. So you're trying to go through this neural network. You want to get information from this layer and predict, which one has a higher probability to be lightened up. If that one is one of them has a pretty high probability, you can make a prediction that, hey, this very likely this image is probably containing one of this character. Okay, now the magic happens now, assuming I have 3 here. Now, my 3 is not very good. But the model gives you 2 guesses. First guess is 3. Second guess is 8. Both are actually close, right, to some extent. So again, this is a pre-trained model. All the weights already there. But this shows you all the feature maps, which is quite impressive for you to see how things are working. This is my input, as actually just copied my input and create this matrix, matrix to represent each pixel of my input. Downsample that. This is like a very smooth. I believe it's more than 32 by 32, but here it converted my input into 32 by 32, or I believe 32 by 32. And I needed to zoom in a bit more. You can use, okay, let me show you. It's really, really powerful. Let me see. Okay, let's go to the first pixel here. Okay, so what this one does? This is my input image. That's this like a small filter. This picture is 1, 2, 3, 4, 5. This is a 5 by 5 filter. This is already trained. This filter has been trained, so that's why its filter looks like backslash or slash. This is a slash, kind of like slash shape. But the image is, my current image here, its scaling is empty. Let's move a little bit to left so that it's here. Input image. Okay. So the input image here, since I'm pointing to this pixel corresponding to the input image at this area. Let me turn let me clean it up. Probably 2 here. Then you have something to see. As you can see here, this is my input image. When I'm scanning, every point, every 5 by 5 area will be multiplied element by this one and give me the final output here. So every output is a kernel scanned by that. Giving me one kernel, I have one feature map. So essentially, I have 1, 2, 3, 4, 5, 6 feature maps in this one. So I have 6 kernels. That's the first layer. I apply the feature maps to my original image. I get all these 6. Now, if you look carefully, this filter is this shape. And everything along this picture, the filter is the same. As you can see that. The filter is the same. It's just the input image is different. Of course, output will be different. Then if I move to another feature map, the filter is the same, but the input image is different. Now the final output will be different. As you can see, on the second layer, this feature maps on the second layer representing the results after I apply the feature map to my input image. Each feature map representing the results when you apply different filters to it. If you put your mouse on each one, you'll see the filters actually look different. This filter, as I mentioned, is already trained, so you have totally 6 filters. This one looks like a backslash, and this one looks like a slash, as you can see, right? It's different. That's the first layer. So apply the convolution neural network layer to the first one. Now, second one is using max pooling. I take 2 by 2 pixels from the previous layer and find the maximum value and save it there. And you can see there is for every feature map, I have 1 max pooling image there because this is only doing the downsampling. It will be 1/4 size of the original one. The next one, you do another filtering, but this time you take multiple feature maps and apply multiple filters there for each image. This is a little bit different from the standard Yang-LeCun, it's called a Le light, which is Yang-LeCun light. I'm sorry, this is the one a little bit different. From Yang-LeCun, especially it's taking this individual features and apply it for individual map, but this one is trying to use multiple feature map as the input and constructed a filter like that to apply to it. But again, it's a similar idea. It's just like implementation, a little bit different. On this layer, you won't be able to see the letter 2 anymore. It's just so, it's getting so abstracted out. You won't be able to see anything like a 2. Actually, sometimes you can see some shape like 2, right? Then after that, I have another max pooling layer. The reason is that we needed to downsample a lot from this big image to this totally 9 element. And we don't want to lose too much information on every layer. So we don't want to dramatically change the size so that a lot of things got lost. But we want to keep doing that and trying to pull the information from that as much as we can. And finally, we get to one of the fully connected layers. This is a fully condensed, fully connected dense layer like we saw last time. You get every pixel collected from every output from the previous layer. That's every pixel. And find the corresponding weight, multiply that, and get this value. Just imagine how much calculation needed to get all the values for this line. You need to do the calculation for each one of those. Each one is a weighted average plus activation function to all the values on the previous layer. Now you have another condensed layer just to further extract information, which is actually needed for you to do some nice mapping. And finally, here we go. This is another fully connected layer. Connect your previous flattened layer to your final output. And then you can make predictions to see which one. This 2 gives you a maximum output, which is a good sign, means it's gives you the correct prediction. This is a very useful tool for you to see how CNN is working. And I think this is a fabulous demonstration about how things are working here. This is a very simple example, but for images, all the regular colorful images working exactly the same way. It's just like sometimes the neural network is getting more complicated. You have hundreds or thousands of layers. There are some other different ways how different layers got constructed, but essentially it's a similar pipeline. You have input, do some filtering, do some downsampling, and do some connected. It's more or less like the same. Okay. So this is another good example. I'll just leave it to you all to play around. This is very, very cool. You can go there. I'll try the 1 or 2 examples so you see how it works. So assuming you have 1, 2 features here, you have different data types. And you can increase number of neurons for each layer. You can increase number of layers. You can also increase layers, neurons, etc. You can, depending on complexity of your model you're training, and you can start training the model. The model will try to find a way to classify. This is the classification problem. Classify your data. This is already working pretty well. If you look at this one, it's classify your data points, in a very nice manner. If you're using as a supporting vector machine, like what we did last time, it's more or less doing a similar job. About this one, this is a bit more complicated. You cannot easily do this with a linear method because it has a very nonlinear shape. But neural network can do this for you. The tricky part is the last one. I think I tried it the other day. This one's never working for me, no matter how hard I try. You can explore this. I tried almost all the possibilities, but totally you can get up to 8 layers, 8 neurons per layer, and multiple 6 layers or more. I think 6 layers. That's maximum. It's still, I couldn't get this one worked out properly, but you can try it yourself. Only right, there are many other, you can try different. I'm sure. You can play with this. This will give you a very good first-hand experience about all the networks. Okay. Since I think we're definitely running out of time, but it's good. It's okay. No, I'll leave all the exercises to you all, and you can try things out yourself. Not too complicated. Running just neural networks is fine. So I'll quickly introduce Keras, and then I'll get you through some of the simple examples. You can try out the more complicated examples later on. There are a couple more there attached to this this slide deck. So Keras was it's kind of interesting that it's a package developed by a Google employee when he was working at Google, and then they started a non-profit organization called Keras.org and etc. that developed this Python-like interface that utilize not only TensorFlow but also some other modules. So Keras back then just provided APIs, so they're not implementing anything themselves. They're just using other functions to implement all the layers and other structures to build neural networks. One of the major reasons why the Keras is there because TensorFlow, as I mentioned, TensorFlow 1 is not very welcomed by the by Python community, because the way how it's writing the TensorFlow code, you still need to compile the computational graph first, and then you can run it. Not like Python. Every time you get something, you can run it and get something results back. So it started writing as this interface to use TensorFlow Microsoft CNTK, which now I think it's not maintained anymore because Microsoft is switching to other frameworks. Theano is a very famous deep neural network package maintained by a Canada research group, but now I don't think it's maintained either. The Theano team is more or less migrating to PyTorch, and that's another big chunk of a big big branch of framework. But today I just focus on Keras, which is can be considered as a TensorFlow 2.0, because in TensorFlow 2.0, it started migrating to the Python-like interface, and the recommended API is actually is a Keras APIs. So basically, TensorFlow is using Keras as its front end and using all the stuff in the backend, etc. So that's essentially we have back then. I think Keras now it's more or less merging with TensorFlow. So, but just not so long ago, probably sometime last year, I heard that Keras also providing APIs that you can use PyTorch only. So essentially, Keras is still building on top of 2 very famous frameworks, and you can leverage the functionality for both as if you're writing your deep neural network in the Keras APIs. So you can use either TensorFlow or PyTorch, which is good. This is some. Let me see what this one is. This is some of the connections between all these keywords. I did a quick search on Google and use this visualization do the diagram. So just like many other machine learning models or deep data science models in general, you start by preparing your data. After you get trained data ready, you define your model, and then you start configuring your training parameters. You want to tell your model training process how many core, not how many layers you want, what number of, how many neurons per layer, things like those, and also providing the optimization function you use to minimize your loss function, and also your metrics that you use to evaluate your errors, etc. Those should be defined in the training configuration. So after that is done, you simply just dot fit, and that's basically the training process. And then your model got trained, your weights got saved. Next time when you call it, you just call model predict, and your model is able to be called in and then start doing some prediction for you. So that's basic workflow. There are some building databases in Keras, just like scikit-learn has some building databases. You can use that for testing and other things. Like MNIST is already building database, building into Keras, like building data set. There is also another interesting one called a fashion MNIST, which is containing 10 different fashion categories that are used by Sears. I know Sears claimed bankruptcy a couple years ago, right? And they use all the icons Sears used to in their advertisement, which is a kind of interesting set of buttons you can like icons you can use. So there are many other examples you can utilize. This is the way how you use the dataset provided by Keras. Simply just import this particular data phrase in the database, and then you can do the load the data function call and get the data automatically splitting into train and testing, and that's it. That's how you get started with all the preloaded dataset. If you have your own dataset, you have to do the cleaning and other things yourself. Do some normalization, do the splitting. You can use scikit-learn to help you on that. And as I mentioned, when you're dealing with different data set, you need to look at the data type first to figure out what kind of model you can use or what kind of method you want to use. For categorical data, the pretty common used technique is to do so-called one-hot encoding. It looks like like trivial, but actually it's actually very useful if you think about it. Instead of using dog and cat and horse as individual indicators, or you can just use the numbers like 1, 2, 3. But as I mentioned, all the numerical values, whenever you do some training, this gives you some trouble because 1, 2, 3 itself, themselves are numbers that are different. You can do, you can do some things with numerical values, but that doesn't really representing the independent categories and each value carry. The best way to do it is called one-hot encoding, is to create a vector. If you have 3 categories, let's create a 3 element vector. Dog, assuming it's the first one, I can use a 1, 0, 0 to represent dogs. Kind of like a basis functions. Basis is in a 3-dimensional space. You have 3 dimensions. The first element is just 1, 0, 0 representing the x vector, unit x vector. 0, 1, 0 representing the y unit vector, and the 0, 0, 1 representing z unit vector. Very, very similar idea. You can do that. Of course, you have one more dimension. You just add one more dimension to your vector. It will be 1, 0, 0, 0. If you have one more category here. This can also, if you look at this carefully, this can also representing the dog here is 100%. If you just like 100% dog, 0% likely to be cat, 0% likely to be horse, this exact same vector could be used as a final output. If it's, say, 0.8% dog, 0.1% cat, 0.1% dog, a horse, you are very likely to have 80% to be referring to a dog. And it gives you a direct mapping to the mathematical functions you use for predict which category it belongs to. Right? Numerical encoding, it's sometimes also working depending on the numerical method you're using or the machine learning method you're using. But this is the most commonly used way to do categorical data. You can use a machine learning model to help you to deep neural network to train your model to predict the one-hot encoded output. Okay, with all that said, this is all. When you create this simple neural network, this is all you need. 1, 2, 3, 4, 5, 6, including this one, so like 7 lines of code. 1, 2, 3, 4, 5, 6. Yeah, 7 lines of code. And that's it. That's your first non-trivial multi-layer perceptron dense neural network. So you have input, output. And your input dimension already given here is 20. For example, you have 20 elements in your input. Could be, whatever. It could be a vector of 20 elements. And that's the input dimension you already given. The dense layer is will be providing this more or less the last one. This shouldn't be the output. This should be including the output here. Should be the last one. Should be 10 here, and then you have 2 more layers in between, which is one of the 64. I'm just use this for example. 64 layers, 64 neurons in one layer, and 32 neurons in another layer. So 20, 64 neurons. 32, and finally you get a 10 output. The activation function needed to be softmax because you want this function to map your final weights into a number between 0 and 1. So you can use this to as a probability, even though it's not exactly technically a probability, but to give you the number mapped to the 0 to 1. It will be relevant to your probability. And that's it. You can tell this, what's the activation function you want to use. The ReLU is just the one I showed you, which is 0 when x is less than 0 and x when x is greater than 0. And given that definition of activation function and the dense layer, it already knows the structure of dense layer. It's just fully connected layers anyway. So you are defining three dense layers in a sequential manner. And you can use this as a Python list, telling Python, you can add more layers. It's just like any one element inside your list. You can telling this sequential constructor to build a neural network like that. I don't know. I just start. Yeah, there's like a rule of thumb is that depending on how many input and how many output you may have, the more output you are predicting, the more input you have, you definitely want more neurons to resolve those fine structures. There's no free lunch. When you want to resolve more details, definitely need more parameters to give you the resolution. Right? If your feature, the thing you are predicting is not so many information. There's just a couple of categories. Here, you don't have so many samples. For example, you don't have so many dimensions, not samples, dimensions. The data set itself is not a problem. The dimension inside the data set is most important. For example, image here, for the 32 by 32, you already have like 700 dimensions. That's a big, right, dimension you need to deal with. You won't be able to, you can, but you won't be able to get very good results with a very small number of neurons here, because that's just not enough for you to express the details inside of this input and give you the good results. It's just based on the degree of freedom in your input. And again, the good practice is always starting with some more layers and more neurons and gradually reduce them to see if you can dramatically you can keep the performance while dramatically change the number of neurons layers. Remember the AIC? We're not getting. No, I'm sorry. I taught this in another course. So there's a very famous metric that you can use to roughly estimate. It's simply just a number of parameters minus error. So of course, the less the error, the better. And also, you also want to minimize total parameters in your network. That's one of very important metrics for you to measure the quality of your model. You don't want your model to have tons and tons of parameters and predict something tiny. You want your model to be perfect in the sense that you don't want it, you just want a sufficient number of parameters for you to predict the value at a given accuracy. It's called AIC. I forgot the name of and the BIC, metrics. What's the B? B is Bayesian, exactly. Bayesian information. That's kind of similar criteria could be applied here as well. You can use the parameters here, like a k and minus the log of the error, whichever, to estimate give the criteria. So, let's see. Okay, we still have time. So the compiled models. When you compile models, you need to construct the model telling the Keras runtime library, then what kind of optimizer you want to use for you to do the optimization of this final loss function, so that you can either using there are multiple ways. Some of that don't even know the name. Like this is root mean square proportional. This is a stochastic gradient descent. This adaptive. I forgot this as a gradient descent. This adaptive. Momentum or something like that. So there are multiple ways for you to go from your original random guess to the minimum of the loss function by changing your weights and biases. The different systems or different data sets or different problems, the different optimizers might be working differently. Some of them are working good for computer vision problems. Some of them work good for some regression problems. But in general, this ANDM is pretty commonly used. If you don't have any preference, you can start with ANDM, and then you can start tweak around to see if others will work better. A loss function, there are also, if you are doing the regression model, again, neural network can work with the regression model. Mean square error and mean absolute error, this is simply just numerical errors. That's exactly the mean square error definition that we talked about previously. And then if you're doing just also square logarithmic error, it's similar to that squared, or it's just take a log of the squared. But these two are different. These two are more about categorical data set. When you do the classification problems, you cannot simply calculate the error based on the numerical values because you don't have numerical values. You can calculate the categorical cross entropy more or less like a distribution of the prediction prediction you made with a test data set as an expected test distribution of the test data set. Kalbach Leibler divergence is more or less like also measuring the difference between two distributions. These two could be used to estimate the error for categorical problems. And if you want to dig deeper, each one could be relevant to a couple papers you can read. But they are all simply, in this case, it's just a numerical representation about how big the error is, and how what you use to measure your loss function, etc. Finally, this measurements metric gives you accuracy about your model. For the regression model, it's straightforward. It simply just predict, because you already know the mean value, you already know the expected value, and you can easily estimate that based on the mean, square, error, etc. And then you can estimate accuracy. You can also, this is probably for the logical reasoning or logical regression. You can also use the categorical accuracies. Basically, this one is simpler actually, because these 3 images belongs to the certain group. But if you give me a wrong prediction, then you are correctly predicted only correctly predicted 2 of them. So the accuracy was simply 2 divided by 3. So that's how you do the categorical accuracy estimation for classification, because that is relatively easy to measure. So train and evaluate this Keras model. It's a bit like engineering work. You need to tweak some of the parameters, like how many epochs you want to train, how many times you want your model to pass through all the data you have. That's the number of epochs. And the rule of thumb is keep training as long as you can, but you keep an eye on the validation error. Whenever the validation error is starting picking up, that means your model probably started being overtrained. You want to stop there, because when you're training further down the road, when you're training more, your error will be higher. There's no point to train that way. Batch size is highly depending on the memory you have. The more batch size, that means you want to read in all the images all at once, or all the data all at once. How many data points you want to read in all at once for the training purpose. If you have a lot of memory, you want to train faster, you definitely want to read more, but sometimes you don't want to read too many images because your memory cannot handle it, or your model might not be well designed to handle multiple images all at once. So this evaluation function inside the Keras, after your model got trained, you can evaluate that and return the loss value and the metrics value, and so that you can easily check during the training process. You can easily check if your training errors and validation errors during the process. Okay. So after you do the summary, this is like after you get the previous model you trained, and you can easily see how many hidden layers you have, and each hidden layer how many parameters you have, and also it gives you a total number of parameters, etc. So, of course, this is a very, very simple dense layer. If you have thousands of layers, this summary will be multiple pages long, and it's kind of hard to read it through. But so after you get that model trained, the next thing you want to do is to use it. The function predict is, after you get the model trained, everything will be stored inside this model object. You just need to call model.predict, and that's it. But the predict input will be either new data you have or whatever data you have to make a prediction. So you need to take some input and predict the output for you. This get weights will give you a list of all the weighted tensors. Usually you don't need that unless you want to take a look at the weights yourself. Usually it's just simply numerical values. There's not much you can learn from those weights. And you can also return the representation of the model as a JSON file. And you can also save the weights to different files like HDF5, like hierarchical data frame structure, etc. So after getting model trained, essentially you have 2 files. One of the files will be the weights, which will be just numerical numbers only. Another file will be a structure about your neural network. So when you start using the model, it will load your file structure, also load your weights, combine them, and build a function for you. This function will be the nested function I mentioned. It will be a nested function you use for your prediction. So one of them is architecture, neural network architecture. Another part is a weights for all the neurons inside the architecture. Combine both, you can go all the way from left to right and build the whole function. And that's how you do the inference. The same goes for larger models. It's the same idea. You get weights, you get neural network, put together, you build up your neural network. When you do the inferencing, when you tap in anything new here, hit a enter button, the model will take your input and pass it through the neural network and predict some output for you. Your larger model is working exactly the same way. It's just like a different way of doing. We still have some time, but I'm not sure if we have time to go through all these examples. But I have 3 examples here. The first one is just going through a very simple example for Keras. The second one is just going through the handwritten digits with Keras. The third one will be the fashion icons I mentioned from Sears catalog. I think you can take. It's very interesting catalog. You can use Keras to do the classification for different data set. I can go through this very, very quickly, and then we jump into the third one, because second one we already covered a little bit in the class, so we are in the short course, in the workshop, so we don't need to worry too much. Let me go through this one quickly. Hopefully, nothing will break because this driven node has been there for a while, and I don't know if the Calamity already updated some of the current modules. It might introduce some thing. The first example, I try to show you how to use the Keras to build a regression model for linear regression. This is more or less like something I showed at the very beginning. See, that's the problem. Sequential dense layers, not iterative. Well, I needed to sort this out, but this is the original scatter plot. I use scikit-learn to have a linear regression model to do it, but I can probably go back to the original first peak. You can find the dense model. I can copy over here. It's the same model. It's just like the way it's how it uses different. So it's exactly the same first peak example I showed you at the very beginning of the workshop. It's now we are drawing all the way back, draw the loop back to draw the circle back to the original example here. But you can go back to the first peak example and check it. I'll update this one later on. So the third one, I'll skip the second one. Second one is just something we already talked about, how to use the MNIST. No, actually, this one's not loading directly to. 1 second. Copy image address, I think. Edit. No, I think it's going to. You can click this open in clamp. This is probably the wrong button I copied. You can click this one. It will open up this in Google Calamity. This should be the link. I'm sorry. Now, if I show here. Okay, now it's pointing to the Google Calamity. So this is advanced machine learning driven notebook I developed for another course for master students a couple of years ago. Let me just run this. Hopefully this one will run. I haven't. This not only give you an introduction about this this driven notebook, but about the deep neural network, but also give you an example. It's this one. Don't forget about this one. Let's go to the next one. It's also copy paste some of the slides here, and you can define signals. I updated this one. This also showed you some other activation functions that we didn't cover in the slides today. But I really want to get into the final example here, but final example is this trend. This is MList example. Why it's where is the other example here? T-shirt. Okay, this is the T-shirt. So it's trying to first download this training data set T-shirt. This is a modern sexy Keras data fashion MList. Okay. So it will do, it's exactly doing the load data. It will split the data into these two parts. And then you can check, actually this one is like 60,000 samples, 28 by 28, that's the size. The data type is just unit, just integer numbers because it's just images using integer numbers. You can do the normalization because it's images. We know it's all the RGB value going from 0 to 255. That's why I just simply divided this 255. I'm guaranteed to have a value between 0 and 1. And this is just showing you just one example. Looks like a coat or hoodie. I don't know. I cannot see it clearly. It's a very small image. And this are showing the training data set. These are like different categories. These are not using this one hot encoding. Simply give you the category, particular number 4, number 7. Totally we have 10 from 0 to 9, probably 10 categories, 0 to 9, 10 categories. So each one is representing which category it belongs to. Okay. So these are corresponding class names for, first one is 0 is referring to T-shirt, trousers, and pullover, dress, coat, etc. This is like 10 categories of data. And the first one, the class name is just simply coat. So you can check the shape of the validation area. Our validation data is about 5,000 data. We have test with about 10,000. So this shows you a very quick overview about all the data set. Just icons here. And then you build a model. It's simply just dense layer, 2 hidden layers, one with 300 neurons, another one with 100 neurons. And then we do some model training. And these are the layers I created. This is a summary of the data we have. As you can see, a lot of parameters, not just the ones we saw before. And then this will be the shape, how they are called, etc. And then we have hidden layers, and then we run them. These are showing you the weights and the shapes and the biases, etc. Then you compile them by defining the loss function optimizers and the metrics. As I mentioned, you can use random SGD, stochastic gradient descent is also another commonly used optimizer. Then you can compile them and train them. This will take some time. That's the training happens. I don't think will wait here, but you get the idea. This one, I'm not sure this one has the, we have the regression MLP. I'm not sure this one has the regulation. Okay, this one doesn't have a CNN. Okay, the other one might have, you can go to the middle example, but the basic idea is simply just to get your data, prepare that data, normalize it, fit it into the model, and configure the model, and then train the model. So all the mathematics and all the basic ideas are exactly what we talk about. It's just like, how different neural networks, different neural network frameworks handling all the data and training process are dramatically different. So all these are like a good testing, learning examples. You can get your hands dirty when you have time. So I think that's all for today. I don't want to waste your time, but thank you all so much.